Okay, next topic is the communication strategy for a cooperative cluster. In the lecture part before, we assumed that the devices cooperating, they can always hear each other, right? And also that the link is very ideal. If you send a packet, you will also receive it. The question now is, how can we really deal with imperfection in such a scenario? Here's a link for a paper. I invite you to read this. It's online available. If you have problems with that, we can even give you the PDF over OPAL. Now, the idea is to look into a certain scenario, and that's exactly what we had before, where we had one cellular network pushing out content, and we would like to understand what is different if this kind of content that we are sending out is uncoded, and what is if this is coded, what if we have cooperation, and what if we have cooperation and coding in that. You need to know a little bit about coding here, but I will give you a 101 of that, what you need here. Otherwise, you also invite to go to the lectures of network coding to get a little bit more insights. Now, this figure we have now seen many times. This is the reception of multiple people in this football stadium. What if we would seat cleverly in the stadium? What cleverly seating means, you will also get a small lecture on that. But what if you now get information from there and you want to disseminate it? How can we do this in a better way? So it's also not only an American problem, right, that you see here is a German picture from the Oktoberfest of the data rate over 2 weeks. And you see that the data rate will increase year by year. It would be nice to get a better update on this picture. I will ask for it. So the idea is now, how can we bring a certain number of packets, so P1 to PG, where we call it a generation. So they belong together for a certain content. And the source has now a G of these packets, and they want to distribute it over an base station, whatever, to the receivers, right? We have a N number of receivers here, and we have G packets. And imagine you have a broadcast medium, right? Which means the source sends it out once, and the receivers can listen in or not, depending on whether the channel is error prone or not. So talking about errors, these links from the source to the receivers, we assume a certain packet erasure probability. So with a certain probability, the packet will not arrive, right? So we also say that the probabilities E1 to En are assumed to be independent. So they can have the same value, right? Let's say 5%. But when this guy will lose a packet, it has no correlation with the other links, right? This is an assumption you always see in all the research papers. And what we did is first we wanted to know whether this is right or not, right? So here's a paper we did with 802.11 BG technology on mobile phones. I would just want to go quickly through it. What you see here is Morten, one of the PhD students, who put on each of the red boxes mobile phones. And then we would sending out from the first phone to the others and would like to understand what can happen here in erasures. Another setup was that we had here an access point, a red one here, and we have a sniffer on the other side, this green one, and then around in an array by 3 by 3, we put mobile phones. And then we wanted to know how are the losses. So this was a pattern. The positions here 1 to 9 tells you where the mobile phone was lying. And so device number 9, which has a very bad reception of packets, was lying even on this position on the left right corner. A very good one was 7. It's on the up right corner. And you see, this is quite heterogeneous, right? There are different tests, 10 tests have been done, sometimes better or worse, but you see they're way worse than, for example, other devices. Even 3 and 2 and 1 does not look so good as, for example, 6, 7, and 8. But as this is wireless, it also depends on the position. So if you change now the position, you will see the 9 has now gone from the right lower to the left lower corner, but the performance is still the same, right? It's still bad, right? While number 3, changing the position, has also yield better results here. So first of all, devices are different in the quality. So it really can be that you have a mobile phone that is what we call a Monday product, which was not really well tested, whatever. It just needs to be the solder towards the antenna that makes the device not as good as others. The other thing is we looked into the correlation, and these are some results from the paper. I will not go into detail what they really mean. It has to do with the power values and line of sight and non-line of sight. And the red curve here would say we are linear independent, right? But in all of the plots, some of the really interesting plots, they will tell you the erasures on the 9 devices that you have seen beforehand, they were correlated, right? Nevertheless, if you go back to the example we had for the analytical model, it's easier, and therefore all of the papers you will see, they will assume it. They will say, yeah, this erasure probability is independent from each other. But you have to have in mind that this might be not the case, and don't be surprised if you do real measurements. Okay, so how can we convey now these G packets to the N receivers, right? And the easiest way is an uncoded broadcast. What does it mean? I take packet 1 and I send it out. And once the packet is obtained, an acknowledgement will be sent back to the source. Let's assume that this feedback channel with the acknowledgement is ideal. Problem is here, and we don't put this under consideration, that you need a lot of acknowledgement. In the football stadium, you will have over 100,000 devices that for every packet have to send something back. And this will have a negative impact on the channel as well. So now what you can also do is to say, what you have to look at is how long do I have to repeat this packet P1 once it will not be received. And the problem is, it might be a problem that one has it and the others don't have it. So if you send it out for the first time, let's assume the receiver 1 gets it and the others don't get it. So what the source has to do, it has to repeat it. And it has to repeat it until the last guy has it. And here's the problem. You remember the mobile device number 9 in the slides before. There might be one guy in the stadium who has a really bad phone. He has it in the pocket, or the soldering was not done nicely. So the source will be busy in sending out this packet number 1, which is not very nice because it will spend energy in doing that. But also for the others that have received packet number 1, they always will receive again and again and again this packet. And we have to continue until everybody has packet 1, right? And talking about the duplicates you will receive. So if you are the lucky one that got it maybe in one of the first transmissions, but the source is resending the stuff, you can see how often you will receive such a packet by the so-called coupon collector problem. Yeah? So if you would share your Pokemon cards versus buying, you see this here, buying you would require a lot of more cards than in sharing, which is more or less the minimum one. But what we are doing here is more, we are on the buying curve here. But we would like to be on the sharing curve, right? And how can we do this? Here coding comes into the picture. Now the source will will not use these kind of packets, it will create coded packets, right? As a linear combination of them. And then send some packets to the receivers until all of them have received G packets. But now the good thing about the coding is that you don't need exactly these G packets, you need any G packets. And what is also interesting, we will only send an acknowledgement when we received G packets, not for every packet. So we even cut down on the number of acknowledgement by the number of G. Good. How can this be done? Just in a nutshell, what you can do is you have here your original packets, P1 to PG, and you have to look for a coding coefficients, and then you get coded packets out here. Now, this can be done in different way. We are choosing here random linear network coding. You can even use Reed-Solomon. In Reed-Solomon, your coding coefficients are well defined and deterministic, while when you use random linear network coding, we randomly choose this kind of coefficients. For the cellular exchange, it would not make a huge difference here. Some people might say rateless versus not rateless. You don't have to know at the moment what this means. But the interesting thing is that this random linear network coding has an advantage later when we are talking about local exchange in the cooperative cluster. So when you get these coded packets out, these are the linear combinations of the P packets over some coefficients. And what you can do is, if you have G packets here, as we had before, you can create a matrix with exactly G randomized coding coefficients, and you can, at least you have to go G in a row, but you can even create more, as many as you want. It's randomized anyway. You can continue and continue, and you get out at least G packets, because this is the minimum you need, but you can get more and more and more. And you see where the advantage is. If you have a lot of devices where they are waiting for packets, then you call this a rateless code. So you don't have to restart from the top. I said before that we will always take the always take linear combinations. If you want to make it very easy, you can even force the first matrix G by G to be an identity matrix where you only have ones here and the rest is 0, which means that you would have P1 to PG here and then start with the coding, which is a little bit more energy efficient for the source, and also for the decoding it makes a little bit of sense to do that. But this is a specific form called systematic coding, as you can see in our lectures on network coding. Good, just an example what we mean by that. Imagine you have 3 packets and you want to send it out, and the first time we send out P1, and the station 1 will not get it. P2 and P3, the station 2 and 3, they got it. Then I'm sending P2, P3. This is now the systematic code. I could have even sent out combinations already. But now in my last point, what I would have to do in the uncoded phase, I need, as you can see from the pattern, I would need to repeat P1, I need to repeat P2 and even P3. But in the linear combination of these packets, you can even send out a coded version. And this is a representation of all the 3 packets. Like you can see here, the red one is the one you want to send out, and this plus means it's a linear combination. It's like an equation, so it's not if all the packets are 1000 byte that you have 3000 bytes now. No, it's still 1000 bytes, but they are coded together. So now let's assume we are coding from the beginning, because this makes it a little bit easier. We are assuming that we have a certain field size. The field size is more or less the granularity of the randomness in the coding coefficients. If we assume a large field size, then everything will be fine. If you have lower field sizes, you could create something that is called linear dependency, so that you still get a duplicate. Even though you got a packet received, then you need to receive more than G packets. So from now on, we say the field size is very high, so we don't have to deal with that. We could also include this in our equations, but it's not so easy, and it will not help us to understand any more insight for the corporation. Okay, now if I send now a coded packet, and still one will get it and the others don't. So where's the advantage? The advantage is that I will not continue to repeat exactly CP1, right? I will just go to my coding matrix and say, give me a new one, right? So in the next transmission slot, we will just send out a new one. And the good news is this receiver will keep the coded packet 1, and coded packet number 2 is sent out. And this is a totally different representation of all G packets. He has already one, and now he gets it. He will get also CP2, but he didn't get nothing yet. So what will change dramatically is that we continue to send out at least G packets, but as we have errors, we will send a little bit more. And now the good news is we only have to look who's the worst guy that will get the G packets, right? And there we go over whole G, not packet by packet. And this will have an advantage, you will see later on. Now, once I assume that we can also have cooperation, there are two forms of cooperation. Should they cooperate in an uncoded fashion or in a coded fashion? And here we have N receivers. The question is, should all N receivers listen in to the source, or do we select some sort of cluster heads? These are bosses that will listen in and will say, okay, we are the cluster heads and we will cooperate. The advantage here is to have a good number of H cluster heads is that they only will issue the acknowledgements. The others will not listen in anymore. And the others that do not listen in, they also save on energy, of course, right? So they don't have to switch on the air interface for cellular. They just switch on for the short range. So the first question is, why should these heads do that, right? You can change the role now, let's say from one G to the next G if you want. If you build up trust, even maybe multiple Gs, but you can change it among these devices. So these cluster heads or just heads are listening in, and then we assume that everybody can listen here, everybody, for the time being, right? And the N, we had N receivers, N minus H devices are connected only to the local cluster, to the cooperative cluster, and we call them non-heads. So there will be two phases. One is the source to the heads, and then heads to the non-heads, right? And therefore, sometimes we call them cellular, local stage, cooperative exchange, whatsoever. I hope I can say always the same word for the same phase here. Now, if I have an uncoded cooperation here, let's assume that the first one, they listen into the, they need to be feed, and it's like the broadcast phase. You can now take it to say, when can I stop here? And one of the idea is to say, if everybody gets the packet P1, then we can continue. But the situation is easier because now we only have to assume that one of the cluster heads need to receive a packet, because then it's available in the cluster, right? So now you have also to make sure who will say something to the source, what we need here. It's a different acknowledgement strategy, but this is also the one where it benefits. Now, once you have got the packets into the heads, at least once per head, then you have to exchange it in the local stage. So the coordination here, we just assume idle conditions. They see each other, and now they can broadcast them to the neighbors. And if I have cooperation, as I said before, we also get packets in, but now the packets will not just forward it, we are recoding them. Recoding is a feature of network coding, which means if, let's assume both stations, R1, R2 until RH gets a packet. If all of them would now forward this packet, it will create duplicates in my cluster. In order to avoid that, we are recoding. Recoding means all packets I got, I form a new linear combination and send it out. And if there are a lot of losses on the seeding link, then you will understand that now these people are doing good in recoding the packets because they will create less duplicates here. I come back to the point of duplicates for cooperation and coding in a minute. So now we would like to understand how much actually transmission do I need here, right? So let's start with the first one, which is, or let's first start something in general, what all of them has the same. So the number of transmission to send one packet to the receiver J, whoever J is, from the source we call this Tj, and it's a random variable geometrically distributed with a success probability 1 minus E of this specific link, right? If we assume that all links have the same erasure probability, it could be just E. So this means here, if you look at this, this is the way you write it, but it's a probability, and it tells you something about how often did we fail until we got one successful transmission, right? So this is the part, the probability that we fail in the t minus 1 transmission, and the second one is that we have succeeded at least once, right? So we will minimum need one transmission, but we can even think about more transmission due to the errors, right? This is for all the systems the same. If you now look at the uncoded broadcast, so if we take one packet out here, then you can say, what will define our time in conveying this packet to all of the stations? And there's a good news, you don't have to look at them individually, you just have to find out who's the worst of them. So if you look at the distribution, you find out who could be the worst in this case, and this will define the time for one packet. So the worst receiver is then the one that takes the most of the time, and we only have to look at this. And then the distribution for broadcasting the ith packet, TBI, is given by the maximum of n geometric random variables. You can see it here, right? And we are looking only at the worst. So give me the maximum over all j. And then for broadcasting in total, because this is only for one packet, we will say the time we need for broadcasting in an uncoded fashion goes as a sum of all of these TBs, so every time the worst, over all g packets. And does not have to be the same packet all the time, right? But when we assume a large number of devices, you can just say g times TBI, as you see it from here. Now, here you see it. I just wrote it down for you if you are home alone with the slides and not listening to the video. That's saying that this is the that we wait for the receiver with the worst conditions for packet I, and same for the other packets, because there's no difference if I have packet 1 or packet G in there, and the distribution is the same for all of the devices in that time, because we assume that the error rates are independent. It becomes more difficult if they are dependent, because then really you can wait for the crying baby a long time. So this is a quite optimistic case for uncoded, but you will see later it's so worse that taking more realistic assumption would even make this worse. Now, if I do a coded version, now I don't look at an individual packet analysis. I will go by, let me look at all the G packets. And when I have G packets, I assume they're linear independent because of my field size. That should be enough, and then I can issue one acknowledgement. The advantage over issuing only one acknowledgement per generation then for each packet, I hope this is clear, because you don't destroy your wireless medium. So now you have to look into this and say, for a single receiver, the distribution for the number of transmissions to decode all the packets, TRJ, is the sum of the G geometric random variables with the equal success probability. And this is T, that stands for the random RLNC for this station. It's a sum over a packet 1 to G over the individual T values. This includes the coupon collector problem. And this is then realized in a negative binomial distribution, assuming still a high field size. Then you will say, okay, the negative binomial distribution, G, this is generation, 1 minus E, the erasure probability, and it's given by this equation, what you can see here. And this is the broadcast setting, and we could say that the receiver J simply waits to get G packets, linear independent, large field size, and it does not require each packet to be acknowledged. That is what we said. And here again, this is the probability of having G successful receptions, because you need them at least. And then you had certain erasures while you're doing this. So we would need another term here if we would assume linear dependent ones, but we are not doing this. And as these receptions, successful and unsuccessful reception, can happen over a certain combinations, you still have this binomial function over here. Okay, and we need at least G transmission. I think this is clear. So for the broadcast with coding, the distribution for the number of transmission is then T broadcast coded is the maximum of the times for the individual devices. So we look only at the worst station that needs the time for all G packets, right? So we say we depend on the user who takes the longest time to collect any set of G coded packets. And again, underline that we have a high field size. So if we now assume uncoded cooperation as the third case, we have the two stages, and we have to look into the first stage and in the other. The first one is quite clear. We have an uncoded phase of seeding and then an uncoded cooperation phase. So due to the cooperation, just one of the receiver needs to get the packet. And the source only needs to repeat it if none of the transmissions has been successful. So you can say that we have a new erasure thing, e-cooperation, which is a product of all of these individual links to the cluster heads, right? And then you can take this new E and see it as an uncoded broadcast system. And that is then the same as we had before. So a geometric with success probability 1 minus E cooperation. And later for all packets, it's the negative binomial distribution G over 1 minus E, the new E cooperation. So once we have seeded it into the heads, then we need a new phase, which is the uncoded cooperation. And if we assume that not all of the devices, so H smaller n means not all of the receivers are heads. So we have some non-heads, so to speak, and that means that we have some devices that have not received anything, while the heads have already received something. In total, they must have received all the G packets, but we don't know who has what. But the non-heads, they have nothing, right? So if we assume that H is equal than n, then there is something which says, okay, we need only the maximum of the rounded up probability, and this is the number of the packets that must be at least transmitted, right? So because some of them have already received some packets, as I told you. Now, assuming that for the local exchange H is smaller than n, the dominant factor in the number of transmissions are the n minus H devices with no packets. This is clear because for them we are doing the sending out, right? And if they are all cluster heads, we only need a small number of extra packets just to fill in the holes what they did not get in the first place. Because if epsilon is small, you can imagine that then the exchange will be rather fast. The distribution is then, we have two different types here. Without going too much into detail, the top is the one that is for when you have only, if you have non-heads. The other one is everybody is a head. And then you have a part, the first part is always from the cellular transmission, right? With the new erasure probability. And the other one, you know this also where it comes from. It's the local states transmission. And then each receiver disseminates its knowledge to all others. And we are bound by the receivers that need the most combinations. And therefore, you have two different things here. The one is really how many still are in the loop. And here you have this kind of value that I showed you in beforehand. Okay, if you then start the coding, instead of this was uncoded, if you have a coded phase of one, the cellular part is more or less the same, or not, it's exactly the same. And now we have network coding in both stages, also here, and that means we have a small different thing, as you will see later. Just to make some analysis, we have an average number of transmission, and we say the average number of transmission per packet is the time TS divided by G, where S is the strategy. So if you evaluate just all the devices I had, just to make it easy in the beginning, and we assume 30% losses for all of the links towards the devices. Then we also have a certain field size, 2 to the 8. Don't think about it, it's high enough. And we want to have 30 packets, right? And then what you see here is a multicast scenario, the average transmission per packet. How often do I have to transmit a packet to be successful over the number of users? And you see, if I increase the users, then I will also increase the number of transmissions. You see, for example, the blue one, uncoded, goes up dramatically, right? So if you have only one device, you start up here, and then there will be some form of increase also here. The red one is cooperation, but uncoded. The green one is already no cooperation, but coding. And then you have a smaller one down here, which is coding and cooperation. The gains you will see here, they always differ between the settings and the error rates you see here. But you see the best is if you code and cooperate. Now, if we look at the different strategies and we just look into the divided by the broadcast, you see nothing changed here. Coding and cooperation gives you the highest gains, and then the lowest gains, or the second best, then as you have seen before, then just broadcasting is at least that you cooperate, right? So this is the stuff that cooperation can give you, and this is what coding can give you, and then this what both together. Okay, so far we have now looked into the one thing: what is if the links are error prone, but so far we assumed that we only have one cluster there, right? And maybe clusters of the same site. What will happen if the clusters have heterogeneous sizes in a cooperative setting? That will come in the next phase.